Okay, let's start talking about chemistry now. We ended last class, we talked about the Diels-Alder reaction. Our diene has to be able to reach an S-cis conformation. Remember that S-cis is talking about the geometry, about the sigma bond. So about this sigma bond, this thing is in the cis geometry. We need to be able to achieve that. So if we have molecules that can't achieve that, they won't be reactive in Diels-Alder reactions. And you can see this thing actually is a good diene because it is locked in the cis conformation. This thing is pretty good because it can achieve a cis conformation. This thing has difficulty achieving a cis conformation. It's high energy. It reacts relatively slowly, but it still reacts it's a useful reaction. It's a useful compound to do Diels-Alder reactions. This one just won't react because it cannot achieve an S-cis conformation. And you could imagine we could have ring structures which prevent reaching an S-cis conformation. I want to, why is this? Go through some, this is just review. This is more about the reactivity of different dienes. Also, this idea of the energy levels of the orbitals is important. When we have electron-rich things, they will be the nucleophilic component, and electron, in other words, where we have high energy homos, they will be nucleophiles, and low energy LUMOs will be good electrophiles. Typically, we have electron donating groups on the diene and electron withdrawing groups on the dienophile. Okay, I don't want to get too much into this stuff. So we talk about nucleophiles and electrophiles. This is in the loosest sense of the word of nucleophiles and electrophiles. Even though we think of this as being the nucleophilic component, they're not nucleophiles like methoxide anions or things like that. Okay, they're much less nucleophilic in character, but we think of them that way. We talked about orbital overlap, the inverse demand. Okay, this is actually important in terms of synthesis, and we're not going to get into it too much, but I want you guys to be aware that these reactions are stereospecific, and we're almost done with this. So I'll put this. Okay, so we talk about our reaction as being a syn addition across the double bond. And syn addition just means that both components, both of these bonds are coming from the same side. We know what anti-addition is, would mean that one attacked one side of the alkene and one attacked the other. So it's a syn addition to the double bond. That has consequences in that if this geometry is cis, it will remain cis in the product. Okay. Also, these things on the diene component, if they're on the outside, they will be cis to each other. And if they're both on the inside, they will be cis to each other in the product. Okay, so that's the stereospecific part of the reaction. We also have some stereo selectivity indicated there, but I have a better picture of it coming up. So we have a possibility. The other thing that you're going to see is things like this, and we'll talk about this in a second. What does all this mean? So this looks like it's going to be, on paper it looks like it's a flat molecule, and we're indicating that these things are sticking behind. This is above, okay, so that we know that the geometry of these things is trans to each other. The geometry we would describe here is cis. Okay, so we can have two modes of addition, endo and exo. This doesn't, here we have an exo, I'm sorry, oh that's only applying to these. This is an exo addition, and we're saying that the component that was on the diene is above the plane, and this is an endo addition. Let's take a look at that in terms of transition states. What we're saying, this is really, notice how in this thing, this is the endo transition state. This component is under the pi system over here. So this big substituent is under the pi system on the forming ring. For an exo, it's not under it, okay? That has stereochemical consequences, and that is what happens that gives the stereoselectivity. The stereoselectivity is variable. Some compounds are quite selective, other reactions are less selective. There's reasons for it which we won't really get into, but what happens is the orbitals interact of these two pi systems. That actually stabilizes things, and this is actually the preferred transition state. It's a little bit lower in energy because of those orbital overactions. A little bit counterintuitive because we might think there's steric interactions that would keep this from being the preferred transition state, but it's orbital interactions, and we don't need to get into that. So remember I talked about this is a good approximation of the three-dimensional, well, it's not real good. I drew it in ChemDraw, but this is what we're talking about here, okay? So we can see it's a little bit more complicated than what we see here. We often just do this. Remember, the minute we have these are sticking out of the plane, we should realize that these bonds are sticking behind the plane. And we see that here, right? These are sticking above the plane, and these are below the plane, okay? So we need to be able to go from here and at least loosely imagine this, but we really need to, we need to be able to go from here to here. There's something called Grossman's rule, which I want you to take a look at, Google it. Grossman's rule is just an aid. When you're doing reactions, remember there's hydrogens that we don't indicate, right? There's hydrogens coming off of here. There's hydrogens coming off of here that we don't draw. Grossman's rule just says when you're doing some reactions, if you're having trouble, maybe draw explicitly those hydrogens in so that I won't forget that they're there. That's all that, it's really just an aid. Okay, and in today's quiz I'll tell you, feel free to use Grossman's rule, okay? So, by the way, these are just being equivalent. They're not actually alkynes. So be able to go from here to here. These are the same structures, it's just that I've explicitly put in those hydrogens because these are sticking below. If they're cis to each other, the hydrogens, these hydrogens also have to be cis to each other on the other side of the ring. Okay, so when we first start in organic chemistry, we often, we don't see those, so we kind of forget they're there, but we have to remember they're there. So I told you that these are stereospecific, but you can see it's quite variable, and when we get down here, it actually reverses the selectivity, although for a student's standpoint, it gets confusing what we're talking about when we talk about endo versus exo. We're usually talking about the system that has a pi system. So this being underneath would be our endo transition state. And again, I don't want you to worry about this. I'm just setting you up for those of you that take further chemistry. This reaction will be often studied for years to come. It's very powerful because we form two new carbon-carbon bonds. So synthetically, it's a very powerful reaction. This is just telling us now that these reactions are actually regioselective. So if we have components like this and we vary the R group, what we find is that we do get one of these isomers over the other. These are regioisomers. And this one is typically favored. There's theoretical reasons for that, which we won't get into. You'll see those when you take Dr. Lukeman's physical organic course. The same with this. We actually do get some favoritism of the para, and it depends on what the substituents are. But it's very powerful to have reactions that are selective, because we usually want to make, for medicinal purposes especially, we usually want to make one stereoisomer and not have the other ones around, because either they don't do things, or if you think about thalidomide, Google thalidomide, the wrong isomer actually had very serious side effects. So medicinally, if we have a compound that is racemic, we may want one enantiomer over the other, because one enantiomer may be biologically active and the other either isn't biologically active. Can I ask the cell phones be put away, please? Just it's pretty disruptive. Or if you really need to look at your cell phone through class, sit at the back, it's less disruptive. So that's about it for the Diels-Alder. So you can see that there's a lot more that we can get into with the Diels-Alder. We're not going to. I don't want you to be scared of it. Mostly what you want to know is that we can clip together, we can make 6-membered rings from components like this, and we end up with, we have 3 double bonds, our product has 1 double bond. Sometimes we can have acetylenes as our dienophile, they're reactive too. And we're done with chapter 13. The next chapter is aromatic compounds. Okay, so mostly what we'll be talking about at first is just benzene. You guys are used to seeing benzene. Benzene we could think of as a cyclohexatriene, okay, but it doesn't behave like a cyclohexatriene. We're going to learn about that. The other interesting thing about benzene has a real important part in the history of chemistry because there was a lot of theory developed to explain benzene. It doesn't behave as we might expect. And it took people a long time. This is a very famous concept of the guy by the name of Kekulé who advanced the structure of benzene, claims to have had a dream. There's books and books written about this by historians, science historians. Claims to have had a dream where he saw a bunch of snakes and he saw a snake biting its own tail, and that's when he realized benzene was a ring structure, when he had this terrible nightmare. I think it'd be terrible when you're dreaming about chemistry. And I know some of us have had these nightmares. So, okay, we talk about aliphatic and aromatic compounds all the time. Aliphatic originally was the chemical behavior of a compound was fat-like. Aromatic, the compounds had a low hydrogen to carbon ratio. It means that they had a lot of unsaturation. They had some double bonds in them. And initially, aromatic meant, you know, you could smell these things. They had low boiling points and they were quite fragrant. They were very volatile and you could smell them. By the way, if you smell a lot of aromatic compounds, it's not very good for you. Some of them. Benzene is not. Okay. Aromatic has a different meaning now, which you're going to want to take a look at this weekend. So here's some of the structures that were proposed for benzene. It took a long time to actually nail it down. And one of the things that was confusing, I mean, they did come to this cyclohexatriene structure, but what they were expecting was something that looked more like this, right? We know that carbon-carbon double bonds are shorter and stronger than carbon-carbon single bonds, so the expectation was that we would have this skewed ring-like structure because we had 3 double bonds that are shorter than the 3 single bonds. That implied that if we had di-substituted benzenes like this is 1,2-dibromobenzene, we should expect that we'd have 2 isomers, right? Okay, but they never were able to find these isomers. They found that 1,2-dibromobenzene was the same. There wasn't 2 different isomers. And eventually they settled on the fact that all the bond lengths were equal, and that's where this structure comes from. So all of the bond lengths are the same. And we can now describe that in valence bond theory in resonance terms, that's what valence bond theory is, as just being a hybrid structure. The real structure of benzene is a combination of this structure and this structure. Notice we've just moved the double bonds. You will often see benzene written like this with a circle in it. That means the same thing, and that's just saying that the electrons are delocalized around the whole ring. The fact that those electrons, so we have a conjugated system, and our electrons are in a ring, and that actually gives it some special stability. And we're going to just forget about that for a second. One of the things I want you to see is that this phenyl ring, the benzene ring, we find it all over the place. That's what ubiquitous means, everywhere. Okay? We find it in lots and lots of natural products. These are a few things. Look at this. So this is actually what gives gum its flavor and aroma of wintergreen, okay, this compound. Here's vanilla, this cinnamon, okay, cloves, aspirin, okay. We find it all over the place. Sometimes we make these compounds. Here's a cancer drug. We find it. I want you guys to be able to, oops, went the wrong way, be able to name this, okay. This is actually, it's paclitaxel, used to be called Taxol. It's an anti-cancer drug that works quite well for certain types of cancer. It's isolated from yew trees. But you can see that we have lots of benzene rings in there. We also have other 6-membered rings in here. Look at that. There's a 6-membered ring diene. We might be able to make that component through a Diels-Alder reaction. Okay? This has, when I was a graduate student, there was a real race to synthesize this. And it was synthesized. It was a big deal. Someone did a total synthesis of this. So starting with small molecules that you could buy at the chemistry store, it took years and years and cost millions of dollars, and they started off with great big buckets, and the reaction had, I forget how many steps, it was 70 or 80, and they ended up with 3 or 4 milligrams, okay, of that. So it was interesting because at the time I remember friends of mine saying, oh, they've synthesized Taxol, so now we should be available commercially from the pharmaceutical companies, but no, we still get our Taxol from yew trees. Well, through that synthesis, though, they learned a lot, and there's compounds that look a little bit like this from other species of yew trees, and they actually can take those, do a couple reactions on them, and get Taxol. So there's a lot of value in these total syntheses. They learned how to make these from components that look like them through the total synthesis of Taxol, and it actually did drive down the price of the drug. Nomenclature, our favorite thing. So we talk about benzenes. If we put one substituent on them, we can just call it fluorobenzene, chlorobenzene, bromobenzene, nitrobenzene. Okay? All the structures I'm going to show you today, I expect you to be able to name. Some of them will have several possible names. So here we have disubstituted. Notice that we can have 3 different kinds of disubstitution when we just have 2 of the same compounds on it. 1,2-dibromobenzene, 1,3, 1,4. There's another nomenclature that you're going to see a lot. Instead of saying 1,2, we'll say ortho-dibromobenzene. Instead of saying 1,3, we'll talk about it being meta. And instead of 1,4, we'll talk about it being para. You do need to know that, okay, because it just shows up all the time. You can name them either way. I don't care if you call it 1,2-dibromobenzene or ortho-dibromobenzene. Both are acceptable. We have a lot of monosubstituted benzenes that end up with trivial names. I don't care if you know those trivial names. Well, actually I do, because quite often we'll talk about toluene or aniline. You need to know what it is. So you should know these structures as well. This thing, this toluene, you could call it methylbenzene. You could call this hydroxybenzene, aminobenzene. Actually, that's pretty well the same. Methoxybenzene. We could call this, instead of acetophenone, can anybody think of another name? Acetyl or ethanoyl benzene. And this is benzoic acid. When we have substituents on it, we have to number things. If we're going to name this as a benzoic acid, which we probably would in this case, the benzoic acid, the carbon that makes it benzoic acid will be designated 1 by default. So this becomes 2-nitrobenzoic acid. If you called it 6-nitrobenzoic acid, I would mark it correct, but a lot of people would mark it wrong because you just numbered the wrong way. You always want to come up with the lowest numbers as you can. This is 3-methylphenol or meta-methylphenol. And we could even call it 3-hydroxytoluene, right? So lots of different possible names. Here we have chlorotoluene. We could also call it 1-chloro-4-methylbenzene, right? So there's different names you can call it, so don't worry too much. When we have 2 methyl groups, we have a series of compounds known as xylenes. When we buy xylenes, it's quite often we buy a mixture of xylenes. We can buy that. It's just a fraction from a gas plant where they distill petroleum products. We have orthoxylene, metaxylene, and paraxylene. When we have multi-substitution, we either have to give it, remember this is being named as a benzoic acid, so that's carbon number 1. Then the other substituents are then defined. This thing, 2,4-difluoro benzene sulfonic acid. So we've named it as benzene sulfonic acid. That makes that carbon number 1. And then we have 2, 3, 4. Notice we wouldn't name it the other way. We wouldn't go 2, 3, we wouldn't call it 4, 6. Although if you did, I wouldn't be too upset. As long as I can build the compound from your name, I'll give you the. So again, multi-substitution. There we see trichlorobenzene. We have to say where those chlorines are. In that case, 1, 2, 3. This is 1, 2, 4. It's not 1, 3, 4, right? Because you try and keep the numbers as low as possible. Again, I'm not going to get. Now, the other thing is sapling. I think if you get in sapling, they probably are more. Although I suspect they don't have many problems in this way. It's hard to program for all the possible names. It's easy to give a name and ask for you to draw a structure because you should only be able to draw one structure from a name. But going the other way, you can have lots and lots of names. That's why computer-wise, you tend to do it the other way. When more than 2 substituents are present and the substituents are different, they are listed in alphabetical order. Again, I'm not going to get too upset if you don't follow that. The benzene ring itself, when it's a substituent, we talk about as being a phenyl group. So this is butylbenzene, but we could also call it phenylbutane. It would be 1-phenylbutane. The fact that we don't have the number there implies that it's 1. Whenever the number isn't there, it implies that it's in the 1 position. Here we have to talk about where it is, and we also have to talk about the stereochemistry of this model. This is E2-phenyl-2-butene. And here we have 2-phenyl-heptane. So phenyl, and if you ever get a British person talking to you, they'll call it phenyl. They'll also call methyl methyl. So get used to that if you ever go on. There's also other things we name as groups. So when we have a phenyl group bonded to a CH2 group bonded to something else, that's the benzyl group, okay? And we often see it, we just say BN, that means benzyl. You'll see these, that BN instead of writing benzyl because chemists are lazy and they just try to make things as short as possible. And a lot of this is actually because we put things over and under the arrows. That's why we have a lot of acronyms and everything, is so you can fit all that information in a short period. So this is benzyl chloride. We're naming this whole group as the benzyl, and we could also call it a chlorotoluene, if you will, but we probably wouldn't because we have to indicate that it's on that and not on the ring. This is the benzoyl group, okay? And you should be able to get that because it comes from benzoic acid, so it's the benzoyl group. And BZ, that means benzoyl group. Okay, time is going good. Benzene doesn't behave like an alkene. For example, this oxidation reaction, which you would have learned about last semester, and don't worry, I'm not going to test this, but we can make these dihydroxylated compounds by reacting an alkene with osmium and working it up with this stuff, and we get our hydroxides in the cis position. Nothing happens if we try that same reaction with benzene. And in fact, what we find is benzene is much less reactive than alkenes. We don't get addition of bromine. It doesn't oxidize easily. Most alkene oxidation reactions don't do anything to benzene. We can't add water to it like we can other alkenes, right? Other alkenes, we just acid and H2O and we protonate the pi system and end up forming a carbocation that reacts with water to form the alcohol. We can't do that with benzene. We can hydrogenate benzene, but we have to do it under much more extreme conditions. We have to do it at high temperature and pressure under the same conditions. Regular alkene would be hydrogenated quite easily. So the other interesting thing about benzene, we can react it with bromine. Remember, if we take an alkene, we just throw bromine in, and this is very diagnostic of alkenes. We actually see, you probably did this experiment where bromine has color, and if you drop it in the presence of an alkene, the color disappears because you get addition. You guys should know that you get the anti-addition. You guys should remember the mechanism for that. It's from a bromonium ion intermediate. Don't worry too much if you're not knowing that now. Take a look. You'll remember it. If we just put bromine in with benzene under these exact same conditions, we get no reaction. But if we throw in this Lewis acid catalyst, we do get a reaction. We still have to heat it. It's not a reaction that goes really quickly. It goes quickly enough that we can do this in the lab in a convenient amount of time. But to be somewhere around here. It's conjugated. It's a conjugated triene. And what we find, though, is that, well, there's 3 times cyclohexene. We already know that our conjugated systems are somewhat lower. But benzene is actually even more stable than this compound. So there seems to be some extra stabilization of having a completely conjugated system in a ring. So this is much, much lower than we expected. We might have thought this trend would continue and that would be up there somewhere. We're not surprised that it's lower, but we are slightly surprised right now, until we talk about it a little more, that it's that much more stable. So we have, it's 152 kilojoules per mole, more stable than if we just tripled the hydrogenation energy of that compound. Oh, okay, there we go. So let's now think of the structure of benzene. Let's think about it a little bit. We know we have all sp2 carbons, so we could conceivably have everything in a plane, and in fact that is the structure of benzene. They're all sp2 hybridized. That means they all have a p orbital left over. This is what the p orbitals would look like. They're all in the same plane. They can communicate. We can think about it as being delocalized, and this is just showing electrostatic potential map, which I'm going to talk about in a little bit. Oh yeah. Okay, so as it turns out, and we're going to talk about this, remember the conjugated diene systems, we had all these orbitals, and we didn't have any degenerate orbitals. How many people know what degenerate orbitals means? Okay, has nothing to do with their moral character. It means that they're the same energy level. Okay? So when we have 6 p orbitals and we do a bunch of stuff to hybridize or form molecular orbitals, if we have 6 atomic orbitals that we're going to make into molecular orbitals, we have to make 6 of them. There's this conservation of orbitals, right? If we start with 6 orbitals, to make new orbitals, we have to have 6 new orbitals. These 6 new orbitals, these are the energy levels. We get one that's very much lower in energy. These are all bonding. These are all anti-bonding. And we get 2 orbitals that are degenerate. They're the same energy level. These are also the same energy level, and then our 6th orbital is up here. When we put the electrons back in, we see that this is the energy level here. We have 6 electrons. When we make the molecular orbitals, we're able to put all of those electrons in orbitals of lower energy, so we get some stabilization by doing this molecular orbital formation. Okay? And so this actually explains it. Why, though, do we get these degenerate orbitals? We're going to talk a little bit about that. It actually comes about from quantum mechanics. We're not going to get too involved in it. But when we put the electrons in, this is showing a better picture of the molecular orbitals. This is just showing them as how we make them, and this is what they would look like if you did calculations, they would look something like that. Notice then that there's no nodes other than the node that's the plane of the ring. All of them, orbitals have that. These ones both have one node, both of these. Okay, this one's not really easy to see. There's an equivalent orbital of this that's below and the plane is like this. You have a red, a blue, a red, a blue, okay? But we just have one node through that system. These have two nodes. There's a node and there's a node. And here we have a node there and a node there. And this one looks like almost 6 p orbitals all out of phase. When we fill all these orbitals up, this is the electrostatic potential map that we get, okay? Have you guys seen many electrostatic potential maps? I hope so. What this is indicating is the red is telling us that's a region of high electron density. It's actually high. There's negative charges there, partial negative charges, but there's a lot of electron density there. Out here, there's a lack of electron density, and these would be partially positively charged. So electrostatic potential maps tell us a little bit about the charge distribution of the molecule, and that actually informs us as to the chemistry that this thing can do. So this thing could behave as a nucleophile. If it's going to behave as a nucleophile, the region that has high electron density is going to be the nucleophilic site. That's above and below the plane of the ring. We have a lot of electrons that are above and below the plane of the ring. We have a little bit of deficiency out here. Now these are all the little hydrogens bumping off. As it turns out, when benzene undergoes any kind of chemistry, electrophiles approach from the top or from the bottom, okay? And that's what we want to think about, is because that electron density is above and below, that can be the nucleophilic part. If an electrophile approaches, if an electrophile approaches from the side, it's going to run into slightly positive charge. It's just going to bounce off. Might bounce off, roll on top, and then react. Okay, so we want to think of molecules as being dynamic. Underneath this, there's a link to a site that talks about electrostatic potential maps. If you aren't familiar with them, take a look at that. I don't like their analogy that they use at the top, but they have a lot of good pictures. These aren't there, but this is also good. And if we take a look at this, here's benzene, right? C6H6, and we have a lot of electron density above and on the other side of the ring, right? Look what happens when you replace all of the hydrogens with fluorines. We flip it around. Actually, all of the electron density then rushes out to the very electronegative fluoride, right? This is a very stable molecule that doesn't do much because it's not a good nucleophile. We have strong carbon-fluorine bonds. It's just pretty inert. This is a nitro group. Take a look at this and see if you can kind of make sense of those electrostatic potential maps with what you know from electronegativities, okay? So, right, you know that fluorine's very electronegative. Look, it's sucking up the electron density there, making these even more positive.